So in this session, we are going to learn how gas law is used in different applications, and let us first start with the dependence of pressure variation with height. How density of air and pressure varies with height, assuming isothermal atmosphere. So very close to the surface of earth, we will assume that the temperature is uniform and we are going to solve within that approximations. So suppose this is the surface of earth, and suppose we take a element, cylindrical element of at a height of h, or call it z. So this element will have here pressure forces. From this place the pressure is P. As we go higher, the pressure force will become P plus dP. So this is pressure force into area, the force, and due to this weight, the weight here you will be acting downward, that will be its mass dm into g, that is the weight of the element of this gas. So here this width is dz and area of the cross section is this. So consider the equilibrium, of the gaseous element with width dz and area of cross section is A at a height of z from ground. So at the ground we have a pressure equal to P naught, as well as the density of air is rho naught here. So from the equilibrium of forces, so the total upward force must balance the downward force. So total upward force is P into A, that is equal to top force P plus dP into A plus its weight, that is dm into g. So here you see this PA will cancel. So I will write dP into A plus dm is rho, instantaneous at this place density of the gas is rho, and A is the area, dz, so this is the A, dz is volume into g. So you can see here A and A also gets cancelled. So we have minus dP is equal to rho g dz. This is equation number 1, we can say. So now let us apply the ideal gas law. From ideal gas law we have the expression P by rho is equal to RT by M, where M is the molar mass of the gas. So now you see this is our working formula, P by rho is equal to RT by M. So from this we will write dP, or let us simply write rho. Let us write rho, this expression of rho here. So we will write minus dP is equal to, now rho will be PM by RT, and this is G dz. Now you see we have to bring this P this side, so minus P by dP by P is equal to mg by RT, and here, so now we will integrate both side with, when Z is 0 then the pressure is P naught on the surface of earth, when Z is Z the pressure is P. So thus by integrating we will get P as a function of Z. Let us see. So if I integrate it, I will get minus ln this is dP by P, so ln P, the limits from P naught to P, then that is equal to mgz by RT. So this will give ln P by P naught is equal to minus mgz by RT. So we will write P is equal to P naught e raised to minus mgz by RT. So thus we see here that the pressure varies exponentially with the height Z. This is how P varies. Now we can also calculate how the density varies by using this relation. So now let us see how the density varies with height when we assume that near the surface of Earth we have isothermal conditions. So again we will use the perfect gas law, P by rho is equal to RT by M. This implies P is equal to RT by M rho. Taking the differential, dP is equal to RT by M d rho. Let it be equation 1. Now we have seen here from this equation the change in P, that is dP, is equal to minus rho gz. This is we got from this relation. We will substitute, we will assume this as equation 2. We will substitute here minus rho gz, that is equal to RT by M d rho. So you see here minus g M by RT, here d rho by rho, and let us integrate. So all these terms G, R and T are constant, and here it is dz. So dz, z varies from 0 to z, rho to rho naught to rho. So we have minus mgz by RT is equal to, this is ln rho from rho naught to rho. So here again this will become ln rho by rho naught minus mg by RT into z, which implies rho is equal to rho naught e to the power minus mg by RT into z. So you see here both pressure and density will vary with exponentially when we assume isothermal conditions. Now let us see, if we set another condition that if it is not isothermal but if rho is constant, then temperature will vary with Z. So we will see how temperature varies with Z if rho is assumed to be constant, the density of the gas is assumed to be constant.